I already told you some reasons why we want to generalize expected value. Historically, it was a St. Petersburg Paradox invented by Nicolas Bernoulli, 1713, that first time made researchers aware that expected value really doesn't always work, that we want generalizations of it. So here's how the paradox works. We assume a coin is tossed, it gives heads up or tails up. If heads up, you get €2 and the game is finished. If tails, the coin is tossed again, heads or tails. If heads, you get 4, tails continue. Again, with tails, the coin is tossed. This game goes on. As long as the tails is tossed, the game goes on. The first time head comes up, you get the money amount. But the longer it lasts until heads comes up, the more you get. Each time the amount is doubled. So if the fourth time, you would get 16. And this can go on very long, you hope. Question, how much would you pay to play this game once? I give you can stop the video, think about it, make up your mind, and then come back. Okay, I assume you come back now and listen, you made up your mind. To get some idea, let us calculate expected value. And the expected value is, well, you can have outcome 2 with probability half, so half times 2, outcome 4 with probability 1/4, outcome 8 with probability 1/8, and so on. Infinitely often. The first term is 1, second term is also 1, third term is 1, always 1 is added. That means it's infinite. That means the expected value of that game is infinite. That means if you do expected value maximization, you're willing to just to play this game once, you're willing to give everything you own, all the money on your bank account, your house, your car, whatever you owe, everything is worth less than playing that game once. I don't know how you think about it, but empirically we surely find something different. Typically, what people are willing to pay is €4. Some more, some less, but on average, €4 is what people pay for it. If they must pay more to play the game once, 5, then they don't do it. That's the average person. That's, of course, very different than expected value. So surely, empirically, we see that expected value maximization is violated here, but also normatively, rationally speaking, I think everybody agrees playing that game once is not worth infinitely much. So everybody who saw this game got convinced we need a model different than expected value maximization. Well, that was proposed by Daniel Bernoulli. He was a cousin of Nicolas. Nicolas was the inventor of the St. Petersburg Paradox. Daniel Bernoulli proposed a solution, and I say it is called expected utility theory. Many of you heard about it before, but I will still define. It says if you evaluate the probability distribution over money, then it's good to calculate expected value, but you have to reckon that the value of money is not linear. 10 million is not 10 times as much as 1 million. You should incorporate money in a non-linear manner. You should look at the value of money. And that can be captured by a utility function, non-linear utility function, and of that you should calculate the expectation. So then you get the expected utility. And then you choose between lotteries, the one with the highest expected utility you choose. That's how you do it. And as I already said, this can reckon with the utility of 10 million is of course more than the utility of 1 million, but it's not 10 times as much. It's less. The function is concave as we have it. Now, I will show you in a moment that this expected utility formula can give a solution to the St. Petersburg Paradox. But first, let us do some exercise to get some feeling. And again, the style of this course, the algebra is trivial, but still I think it's really good to do it with your own hands. If you do such exercise, then you get a feeling of what the concepts mean. So anyway, we're going to assume the utility of 0 is 0. And the utility of 100 is 1. So we assume expected utility, and these values we already know. How do we know them? For now, just accept this as given. Take my word for it that many of you know, and I will show later that you can always do this. You can always normalize utility as you want. But for now, just give me this one. Just assume that we know this. Assume also we observed here an indifferent 50 for sure, equally good as the lottery between 100 and 0.58 probability of 100. 0.42 probability, 1 minus, of course, is the probability of 0. So we have observed this indifference. First question, what is the utility of outcome 50? Second question, consider 2 probability distributions over money, 2 lotteries. What is the preference between them? That's the exercise for you to work on. So you can stop the video and work on it for a few minutes until you found the solutions and then come back. Okay, I assume you're done now. You're back again. So then I'll show you the solution. And then the first, what is the utility of 50? We're going to use this indifference, of course. It's an equality. The expected utility of the 50 must be the expected utility of that lottery. So the expected utility of 50 is that expected utility. And the latter is 0.58 times now the utility of 100. The utility of 100 is 1 plus 0.42 times the utility of 0. Well, the utility of 0 is 0. So this is 0.58 times 1 plus 0.42 times 0, that's 0.58. And the expected utility of 50, well, 50 for sure means you get 50 with probability 1. So the expected utility is 1 times utility of 50 is just the utility of 50. So from this calculation, we see that these two, we have a difference. They must have same expected utility, blah, blah, blah. We get utility of 50 must be 0.58. Now we turn to question B. There are two lotteries, but now we see for all the outcomes here, and here we know the utility. 100 and 0 we already knew, 50 we just calculated. So we can just calculate the expected utility of these two lotteries and see which is the bigger one. That's the one preferred. So here are the calculations, the first lottery one. The second lottery, this calculation, we see bigger expected utility for the second lottery, so that second lower lottery is preferred. This was in a nutshell. Again, we saw in the first meeting, now we see again this measure predict pattern. Now you have a theory that you assume, you make some observations, and you can predict some other things. You cannot predict how will the choice between these two will be. That's how the theory works. Now let me show you that we can explain the St. Petersburg Paradox using this theory. Here's the St. Petersburg Paradox again, the lottery that you have there. Now we're going to assume expected utility with a logarithmic utility function. And that's the graph. If we do that, then the expected utility of that lottery is half times outcome 2, that gives the utility logarithm 2, plus a quarter times logarithm 4, plus 1 over 8 times logarithm 8, and so on. If you do this infinite summation, infinitely many terms, it will be 1.39. Now it turns out 1.39 is exactly the logarithm of 4. So this means that receiving 4 for sure has the same expected utility as the St. Petersburg Paradox game. That means the certainty equivalent, the sure amount equally good, is 4. We also saw certainty equivalence in the first meeting. Then we assumed expected value maximization. The certainty equivalent was simply expected values. So expected utility is very different. This is, of course, not at all the expected value of the lottery, much smaller, but this is the certainty equivalent. And logarithm, of course, people can have many utility functions, so many people, there's much heterogeneity. And in fact, that was a big reason why Daniel Bernoulli introduced expected utility. He said different people can have different risk attitudes. That was a big step forward. But anyway, under plausible, this is one of the many plausible utility functions. Maybe on average, people have it a bit like that. Then indeed we get the 4 as a certainty equivalent versus the empirical finding. So we explain now that people do not pay infinite for that game, but on average, roughly they play 4. We have explained now that paradox. Okay, we will continue with utility measurement under expected utility, but that will be in the next recording. This recording will stop here.